Good morning, everyone. Thank you so much for attending today. Hope everybody's well out there. I'm not going to say much now. Let's just get straight into the talk. So if you could switch to my shared screen, please. Hi, I'm Martin Woolley from the Bluetooth Special Interest Group, the standards body behind Bluetooth technology, and I'm talking to you today from my home in the UK. Now, my plan is to talk about a number of Bluetooth capabilities and issues for which a deeper understanding of the technology will help you achieve better results. Now, I don't intend to spend a lot of time on the basics, but I will touch upon some of them just to get the ball rolling. So let's get kind of orientated first of all. There are two Bluetooth radio communications technologies. They're branded the same, so this may not be obvious. But the older version is Bluetooth Basic Rate Enhanced Data Rate, or BREDR. It's the original Bluetooth technology from 20 years ago. It's basically a cable replacement technology that enables point-to-point communication directly between two devices. It's old, but it's still the default choice for wireless audio products, for example. Bluetooth Low Energy, on the other hand, is more power efficient, but it's also far more versatile. It can form point-to-point connections, but it can also broadcast data, which allows one device to transmit data which can be received by an unlimited number of devices provided they are in range. And Bluetooth Mesh, which uses Bluetooth Low Energy kind of under the hood, low down in the stack, allows networks of up to 32,767 smart devices to be created, and it's used to create smart buildings, for example. So I'm focusing largely on Bluetooth Low Energy in this talk. So let's start out with some absolute kind of Bluetooth Low Energy basics. So typically a smartphone application will need to discover and connect to a Bluetooth peripheral of some sort. Peripherals do something called advertising, which means that they broadcast information about the kind of device they are or capabilities that they have. And smartphone applications typically start by scanning for these advertising packets and filtering out ones from devices that do not appear to be relevant. So the ones that are selected are usually presented to the user in a list, and the user then picks the one that they want to connect to. Now, the Android APIs include a number of classes which will be involved in device discovery. Bluetooth LE Scanner will be used to kick off the scanning process. Scanning is the term we use for looking for advertising packets, by the way. And you can specify some filtering criteria and other settings, and eventually you get a collection of Bluetooth device objects, and you'll then let the user make the final choice. Now, once you have a selected device, the user has made their decision, you're going to connect to it. And this will almost certainly stop the peripheral device advertising at this point because it's now in what we call the connected state. So once we've got a connection, you're going to be working with a table of data on the remote device called the attribute table. Now, sitting inside this table are a series of things called attributes, basically rows in a table. And each attribute in the table is of one of three types. There are services, there are characteristics, and there are descriptors, and collectively they form a hierarchical structure. Now, services act as a grouping mechanism, and they contain characteristics. Characteristics are really just data items, and they have a specific type which is identified by a UUID. They have a value, and they support various operations that the remote connected device can initiate. So things like reading the characteristics value, maybe writing to it, or enabling something called notifications, which when switched on result in the characteristics value being delivered to your connected application whenever it changes, or sometimes periodically controlled by a timer. And at the third level of the hierarchy, we have descriptors, which only some characteristics have. They allow us to do things like switch on or off notifications, or they provide metadata, which further describes the characteristic in some way. Now, as you can see, you have a bunch of Android classes which represent these attribute types, and the Bluetooth GATT class which is quite important. This provides I'd call it a facade API to the various operations that you can invoke. Now GAT itself is a technical term, and it actually comes from one of the key layers of the Bluetooth stack, and on screen you can see the Bluetooth Low Energy stack that an Android device has. It's got two major components. The top blue box is called the host, and it contains various layers of the protocol stack, and underneath it we have the controller, the grey box, which contains layers from lower down in the stack, partly concerned with controlling the radio, receiver, transmitter hardware in your smartphone. Now, as an application developer, most of your interest will typically be in the top layers of the stack. The APIs you use will largely be driving GAP and GAT procedures and using the attribute protocol to have a conversation between the two devices. So GAP, that's the generic access profile, that part of the stack is concerned with device discovery and establishing connections, and GAT, the generic attribute profile, is concerned with procedures that involve the attribute table. So you'll see the word GATT in some of the API class names, and this is where it comes from. So GAT procedures are executed through attribute protocol PDUs, that's protocol data units, being exchanged over the air. So when you call an Android API, what you're usually doing is driving a GAT procedure, which will result in an exchange of one or more attribute protocol PDUs being exchanged between the connected devices. So what I want to do now is take you through a number of topics, and I'm going to start here and talk about application data rates when transferring data over a connection from an Android device to a peripheral of some sort. So this is a surprisingly complicated topic, and most of the time we don't even care about it because Bluetooth Low Energy devices usually exchange quite small amounts of data. So maybe a sensor delivers a reading of 1 or 2 bytes only, for example, but sometimes we have to transfer larger amounts of data in one go, and if only for the sake of a better user experience, we may want to transfer that data as quickly as possible. So some devices accumulate data when they're in a disconnected state and then transmit all of it in one go when connected to, for example. And there are ways of maximizing the data transfer rate as measured at the application layer. They do involve a number of factors and variables, and a deeper knowledge helps you to understand how to approach this issue and make sense of some of the Android APIs. So first of all, what do we really mean by application data rate? Well, on screen you can see a packet and its contents, and only 2 bytes highlighted in yellow here on my screen are application data. The remainder is made up of fields relating to the Bluetooth protocols that are in use. So the proportion of application data in this packet is quite small, and if we calculate the application data rate using 1 megabit per second as the bit rate used by the underlying radio, then we find that we're actually only getting 95 kbits per second in this particular example. Now, because the absolute amount of protocol data in each packet is fairly constant, it's the proportion of application data in each packet that most influences the data rate as measured at the application layer. So this is one of the key ways in which we can influence the application data rate. The larger the packet and the more application data in each packet, the faster will be the application data rate. Now, we can increase packet size by manipulating something called the maximum transmission unit size, or MTU as it's normally known. So each layer of the stack may contribute data to the packet that is eventually transmitted, and each layer of the stack is subject to a maximum data size or MTU. Now, your concern is with the attribute protocol, since this is what your APIs will be driving, and the attribute protocol has an MTU of its own. So our concern is to make the MTU as large as we can so that we can pack as much application data into each packet. The default MTU for the attribute protocol is only 23 bytes, but if you look at the packet breakdown on the slide, you'll see that 3 bytes of the attribute protocol part of the packet are in fact consumed by protocol data. The opcode, which identifies the PDU type, and an attribute handle, which is an index into the attribute table on the remote device. So you're actually only left with MTU size -3 bytes for your application data per operation. So by default, that means only 20 bytes. Fortunately, only the very oldest devices are limited to an MTU of 23, and there's actually a PDU type called Exchange MTU that allows devices to negotiate a higher MTU value. Now, if you recall my diagram of the stack, sitting underneath the attribute protocol is a layer called L2CAP. Now, this stands for the Logical Link Control and Adaptation Protocol, but that's a great big mouthful, so we just call it L2CAP. This is the lowest layer of the host, and one of its jobs is to communicate with the link layer immediately below it at the top of the controller. Now, the link layer has its own MTU, and it's possible, for example, that the controller is from a different manufacturer to the host, so there could be all sorts of variations. So one of the things the L2CAP layer does is, if necessary, it will chop attribute protocol PDUs into a series of smaller link layer packets using a process called segmentation, and it will do that in accordance with the MTU supported by the link layer. Now, the issue here, of course, is that more packets means more overhead from fixed protocol data, and that reduces our application data rate. So, once again, what we'd really like is to have fewer link layer packets so we get a higher proportion of our bandwidth available for application data. Now, luckily, Bluetooth 4.2 introduced something called the LE Data Packet Length Extension feature, which allows link layer packets to be significantly larger. Both devices must support the feature, and if they do, it's used automatically without you needing to do anything in your application. And the result is that significantly fewer link layer packets are used, and so there's less bandwidth consumed by protocol bits and bytes, and therefore more available for your application data. Now, this is interesting and potentially complicated. What exactly is a connection? So if we have two devices that we've connected by a cable, it kind of makes sense. But when the two devices are wireless, it's less obvious what we mean. So when two Bluetooth devices establish a connection, they have a conversation and a negotiation regarding various parameters that will then govern the way they subsequently communicate. And many of those parameters are concerned with timing. You have one radio, and it's what we call a half duplex radio. It can do one thing and only one thing at a time. It can transmit, or it can receive, or it can be idle doing nothing. It can't transmit and receive at exactly the same time, and only one application can be using it at a given point in time. So it's necessary to share the radio between applications over a given time period, as well as to manage the timing with which the radio is transmitting or listening for packets from the other device. And by the way, some devices contain a hardware radio which is shared across multiple protocol stacks, not just Bluetooth. So the need to share that hardware resource can extend beyond Bluetooth sometimes. So the way Bluetooth approaches this time sharing and scheduling issue is through two concepts: the connection event and the connection interval. So a connection event occurs regularly at an agreed timing interval called, you guessed it, the connection interval. So the connection interval is one of those parameters that gets agreed when the two devices first connect. So when a connection event relating to one of the connections held by our smartphone happens, that's the opportunity for the radio to be used in the service of that connection, with the GAP central device transmitting a packet. That's usually your smartphone first. It then waits for 150 microseconds. This is called the interframe space, and then the peripheral device will reply. And they kind of take turns transmitting, waiting that short time, and then receiving a number of times during the connection event. This is a bit of a simplification, but it's in essence how things work. Now, the connection interval itself can be anything from 7.5 milliseconds to 4 seconds, but it's not the case that the entirety of whatever time period is used will be used for transmitting and receiving packets. The subject of scheduling is far more complicated than is covered by the Bluetooth specifications alone. There are lots of implementation specific issues and constraints. So all we say in our core specification is that at least one packet must be sent and received at each connection event. So there could be a lot of kind of empty space in each connection interval, and you can see some of that on screen there. You've got the 150 microsecond interframe space between packets, and then a whole load of completely unused time, which is a consequence of implementation considerations. So what we can say for sure is that regarding our goal to maximize data throughput, the more often a connection event occurs, so the more often our connection gets access to the radio through having a shorter connection interval, the more often the central device has the opportunity to use the radio and send some data. So it seems reasonable and it is valid to conclude that a shorter connection interval is likely to help improve throughput. But don't forget that you will never see the entire connection interval used for transmitting data. Now, Android has the Request Connection Priority API, which allows you to ask for one of connection interval, including high, which requests a short interval, so that's what we're going to want, but you can't actually request a specific connection interval value, a specific time. So what you get is, in the hands of the API implementation and the device it is executing on. Okay, so some more concepts. Bluetooth is a radio technology, and radio is analog, not digital. We can use it to convey digital data, but radio itself is electromagnetic radiation consisting of waves. And the way that we represent digital data through, those ones and zeros that we want to transmit in radio signals is through something called a modulation scheme. And Bluetooth uses something called frequency shift keying, which involves taking the central frequency in a selected radio channel, and then to represent a 1, we shift that frequency up by a small amount called the frequency deviation, and it's in fact 185 kilohertz usually. To represent a 0, we take the same central frequency and we subtract the frequency deviation, and we then transmit our signal on the derived frequency for a period of time. And that burst of signal at one of those two frequencies is called a symbol, and a symbol is the analog equivalent of a digital bit. And of course there's a rate at which we can transmit symbols. And by default it's 1 million symbols per second, 1 megasymbol per second. And Bluetooth uses what's called a binary modulation scheme, meaning that one bit corresponds exactly to one symbol, or one symbol encodes one bit. So our bit rate at the physical layer is the same as the symbol rate. So at the lowest layer of the stack we've got 1 million bits per second to work with, but that's for both our application data and our protocol data. So, exciting news. Newer devices which are running Bluetooth 5 or later probably support a way of using the physical layer called the LE2M PHY, which kind of per the name gives us a symbol rate of 2 megasymbols per second, which is twice the default rate. Now, the default physical layer, or PHY as we refer to it, is called the LE1M PHY. So you'd expect that with double the symbol rate at the lowest layer of the stack, the application data rate would be faster, and it probably will be, but it certainly won't be twice as fast because there are lots of other variables at play here, which I hope you're beginning to see. If our connection interval stays the same, but the packet scheduler on your phone doesn't take advantage of the fact that using LE2M, each packet takes half the required time, and so twice as many packets could be accommodated each connection event, then you probably won't see any difference. And don't forget that the packet scheduling is an implementation issue that we do not cover in the Bluetooth specifications. So you may not see more than a small improvement in data rate if you use the LE2M PHY. The true benefit of this feature actually is something we call spectral efficiency, meaning that you're using the radio spectrum for less time. So that's actually a scalability benefit, and one which can improve reliability in busy radio environments too. Now, from an Android point of view, you can use the Set Preferred PHY API to indicate a preference. You can say, I'd like to use LE2M, and then if the other device supports the same PHY, you should get that one in use for your connection, but if not, you won't. The last thing to be aware of where throughput is concerned is this. The attribute protocol supports two different ways of writing to a characteristic. So on the right you can see write commands, and they're very fast but they may be unreliable. So that's worth understanding. Ultimately, the attribute protocol runs over the link layer, lower in the stack, and there's a system of acknowledgements at work there. So a device will be informed if its transmitted packet was received by the other device because it gets acknowledged at the link layer. But it won't know if that packet made its way all the way to the top of the stack to your application. You can send write commands as fast as you want, but there could be buffer overflow at the remote device, so be careful there. Be aware though that the very newest version of Bluetooth, Bluetooth 5.2, includes the enhanced attribute protocol, which amongst other things makes write commands reliable through the use of flow control. Now, write requests on the left of the slide here have a corresponding response PDU, and they're reliable thanks to their transactional nature, but they're very slow because you have to wait for each response before you can send the next request. Now, assuming a characteristic supports writing at all, it will support one or both of these variants. If it supports only one, the Android API will figure out the way to proceed automatically. If it supports both, you can use the setWriteType method of the Bluetooth GATT characteristic class to select the one you want to use, and of course, you make that choice based on whether reliability is most important to you or speed. In many applications, a few drop packets really don't matter, whereas in others, it might be critical. So here's a summary. The primary variables and associated APIs that can affect data rate. A larger MTU is going to help a lot. Data length extensions are either supported or not, and they need to be supported by both devices to be available over your connection. They're going to get used automatically if they're there. Shorter connection intervals give more opportunity for data to be transmitted over a particular connection, and so will probably help you achieve faster throughput. The LE2M 2 megabit per second PHY will probably improve matters, but not to the extent that you might assume. And as you can see on screen here, there are APIs associated with each of these concepts. So I did some benchmarking with an Android application that I wrote involving the transfer of 100k of data from a smartphone to a peripheral device using write commands, and working with the defaults that Android provided me with, so that there was an MTU of the default size of 23 and using the 1 megasymbol physical layer symbol rate and the connection interval which I observed to be 48.75 milliseconds using my protocol analyzer. It took nearly 8 seconds to transfer my 100k of data. But when I took control using the Android APIs and chose a larger MTU size, selected the LE2M PHY, the faster symbol rate, and chose the shortest connection interval available to me, I was able to reduce the elapsed time down to just over half a second, which is a huge improvement, as you can see. Now, when I performed the same test but used write requests and responses rather than write commands, as you can see, it took a huge 500 seconds using the default. But once I'd done some tweaking of APIs using the concepts we've just covered, I got it down to just over 10 seconds, which is an enormous improvement, I'm sure you'll agree. So let's talk about range in Bluetooth and low energy next. I think that for historical reasons, most people still think that range in Bluetooth is about 10 meters or so, but that's most certainly not the case these days. Lots of things have changed over the 20-year history of Bluetooth, and range is one of those things. So the first question maybe to answer is, if we want to understand the subject of range, what exactly is it that limits range in wireless communications? Well, it's natural to assume that transmission power is the only variable affecting communication range. It's certainly one of them, and after all, if we want to throw a ball further, we throw it harder with more power. But regulations in the way that radio can be used around the world mean that there's a limit to how high the radio transmission power can be set. It also seems natural to assume that if a device is out of range, this is because its transmitted signal can no longer be detected. But that's not actually true either, not necessarily anyway. So this is how range limits really work. On the screen you can see a blue line representing the strength of a transmitted signal getting weaker as we measure it further and further away from the transmitter. Now, as you can see, it reduces in a non-linear fashion. In fact, it follows an inverse square law. Now, the red line represents the level of background noise, electromagnetic radiation from natural and unnatural sources, which is always there. Now, the problem with range is that the nearer the transmitted signal strength gets to the level of the background noise, the harder it becomes to accurately decode the data in that transmission. In other words, the lower the signal to noise ratio becomes, the more errors we will encounter. And we can actually measure this through a concept called the bit error rate, or BER. Now, the Bluetooth specification states that a BER of less than 0.1% is required. So if the error rate starts to exceed this limit, then we no longer have functioning communication. And it's at this point that we say we are out of range. Now, different radio hardware will perform better or worse in this respect, and the minimum signal strength in dBm at which the BER remains below 0.1% is called the receiver sensitivity. Now, as you may already know, errors are detected by a receiver device using a cyclic redundancy check value which every Bluetooth packet has. But a capability of the physical layer that was introduced at Bluetooth version 5 called the LE-coded PHY goes one step further, because using extra data included with each transmitted packet, the receiver can employ a mathematical procedure called forward error correction, or FEC, and actually correct bits that are found to be in error. So this means that we can stay below the maximum bit error rate of 0.1%, even when the signal to noise ratio is getting very low, and therefore continue to communicate effectively at much longer ranges. Now, in practice, you could achieve up to 4 times the usual range, but be aware that the extra FEC data that's transmitted will reduce the effective physical layer data rate to 125 kbits per second from the usual 1 megasymbol per second that we get by default with other PHYs. So let's summarise the effect of the LE-coded PHY and its use of forward error correction. Without forward error correction, you can see that we reach our maximum bit error rate at a certain distance from the transmitter. None of this is to scale, by the way, and the numbers don't mean anything. But with FEC, you can see that the signal to noise ratio can go much lower before we hit that black line, which is our bit error rate limit. And in fact, over a kilometre is very much possible using the LE-coded physical layer variant, or PHY. There are videos on YouTube if you're interested in seeing people demonstrate this. And in fact, I met a company last year, a Japanese manufacturer of consumer electronics, at a conference, and they presented on the subject of range. And they actually had achieved 3 kilometres in their testing of one of their products, which is pretty amazing. So as Android developers, you have access to the LE-coded PHY if both devices in the connection support it. You've got APIs that let you determine whether or not the local device supports LE-coded PHY, and you can indicate it to be your preferred PHY to use in a connection. But one last thing to know is this, and I've kind of touched upon this already. LE-coded PHY can use one of 2 levels of forward error correction. This is selected by a parameter which is simply called S in the specifications. With S equals 2, and you can see you've got a figurative constant you can use in API calls here. S equals 2 will give you approximately double the usual range, but the FEC data added to each packet doubles the amount of data sent. So your effective data rate reduces to 500 kbits per second from the usual 1000 kbits per second, 1 million bits per second. If you set it to S equals 8, though, you'll get around 4 times the range, which I mentioned earlier, but you'll only get 125 kbits per second because 8 times as much data is involved. So there's no such thing as a free lunch, and there's a trade-off here between range and data rates. Okay, new topic. I'm going to now talk about Bluetooth Mesh, and if you're not familiar with Bluetooth Mesh, this is a relatively new technology that lets you create whole networks of tens of thousands of devices. And Bluetooth Mesh was designed initially for applications like smart buildings. So the Bluetooth Mesh stack is not quite the same as that which is used on smartphones and peripheral devices, which is as shown on the screen right now. It does use the Bluetooth Low Energy controller, but the host part is completely different, with new layers concerned with mesh networking. Now, you don't have this stack variant on an Android device, and there are no APIs for Bluetooth Mesh on Android at this stage. But why would you want to use Bluetooth Mesh from an Android application anyway? Well, consider a smart building full of wireless lights, switches, sensors, air conditioning systems, automated blinds and heating systems, for example. There is a need for user interface applications to be used by people for monitoring, control and configuration purposes. So this is where Android applications can be ideal. But if you don't have a Bluetooth mesh stack and APIs on your Android device, how can you do this? Well, the answer lies in the fact that Bluetooth Mesh defines a number of special networking roles that devices that are members of a network, or nodes as they're known, can take on. And one of those roles is that of the proxy, and it's very simple because a node acting as a proxy has both the Bluetooth Low Energy stack you have on an Android device and a full Bluetooth Mesh stack. So it can kind of translate between those two worlds. So your Android application will scan for proxy nodes which advertise themselves, connect to one, and then send and receive Bluetooth Mesh messages by writing and receiving values over that connection. And hopefully this slide shows you well enough how things work. So what we've got here is a mesh proxy node, which is part of the mesh network. And by the way, it's not a dedicated networking device. It could be a light, it could be a thermostat, it could be anything really. But it's been configured to act as a proxy because it's all software. Now, as you can see, it implements the GATT mesh proxy service, and this service contains two characteristics. One which we can write to over a connection from our application, and we do that to inject mesh messages into the network, and one we can receive characteristic notifications from, and they contain mesh messages coming out of the network. So for the Android developer, everything is familiar and not really any different to discovering, connecting to, and then working with the characteristics on any connectable Bluetooth Low Energy device. The only new things you need to know are a few Bluetooth mesh networking concepts and exactly how those characteristic values are structured so as to properly represent Bluetooth mesh message types, and I'll point you in the right direction for more information on this. So I'd just like to give you a sense of what's involved, and I'm going to show you a short video of an Android application controlling a small network of 16 devices, each of which has a coloured LED you can switch on or off, or whose colour you can change. These are kind of quite common things you'll want to do in somewhere like a smart building where there are lots of lights. Now, something important to know is that Bluetooth Mesh uses a publish and subscribe system. So every node has an address, and there are also things called group addresses. So a node will subscribe to, register an interest in messages sent to a particular group address. If a message addressed to one of the addresses that it has subscribed to is encountered, it will react to that message because it subscribed to that destination address. Now, the way my demo works is that each node has subscribed to 3 addresses. One which all nodes subscribe to, one representing the row that the node is a member of, and one representing the column that it's a member of. So as you'll see, the UI on my application allows me to change the destination address by touching the user interface, and then send a certain message type to either change the color of the light or switch it on or off, or what have you. And according to the address I select, you'll see different subsets of devices in my network will respond. So here are my 16 devices that form my network. Just looking underneath one now, just out of interest, and you'll see a big silver thing. That's just a battery. It's really just a small microcontroller with a Bluetooth mesh stack on it and some code. I'm going to launch the application now and start it scanning for proxies, and it's found one there, so we're going to select that. And you can see that the UI kind of reflects the grid and lets me select rows and columns or the whole 16 grid, and I have buttons for sending on-off message types or color change messages. And as you can see, according to the destination address I've selected, different subsets are responding to the messages being injected into the network from my Android application via the proxy node that we've connected to. So that's the essence of what's involved in controlling mesh networks with an Android application. So where next? If you want to learn more, if you found any of this interesting, where else could you go to find out more about Bluetooth technology? Well, we have all sorts of resources, largely aimed at developers, technical architects, product managers, and people like that. And if you go to bluetooth.com/developer, you'll find links to many of our key resources, including things we call study guides, which are self-paced, self-study educational resources, and which usually include some hands-on development projects. So they're great for developers. There are also papers. Papers are a great place to start if you just want to get your head around some of the theory or understand a new feature of Bluetooth. And some of the key ones that are available are there on the screen. So, thank you so much for attending today, and thank you for listening. I think there should be time for some questions now. I'm also on Twitter though, so if you need to ask me a follow-up question, feel free to ping me a message on Twitter. Thank you again. Okay, so I have some questions on screen. Just let me absorb what I'm looking at here. Okay, so Anonymous asks the question, can you explain why Android must have location enabled in order to have Bluetooth Low Energy included? The answer is yes and no to this. Obviously, this is a decision that Google took. An Android device which can perform advertising. So in my talk, I talked about peripheral devices advertising, broadcasting packets. But an Android device can do that as well. And in fact, generally speaking, the COVID-19 exposure notification applications do this. They involve your application advertising a unique ID, almost like a lighthouse flashing, and then listening for other devices that are doing the same. If a device is advertising, it is making itself known, making itself visible. And much as there are ways in which we can safeguard privacy, the fact that you can use advertising in location-based services of various types. Bluetooth beacons use advertising, for example, I think led Google to decide that we should classify this as a location-related technology. Almost all of the time when you're using Bluetooth Low Energy for an application on Android, it has nothing to do with location, and people's location data is not at risk in any way, shape or form. But that's the way they did it, I'm afraid. Let me see what Dave says. So Dave says, are the stats available on the percentage of devices that have Bluetooth Low Energy available worldwide, not just US and EU? That's a tricky one. I mean, there's sort of two ways of looking at this. First of all, you could look at Android versions and Bluetooth Low Energy APIs. And certainly there are stats available for Android developers from Google about the proportion of those different OS versions that are out there in the world. And if you know, for example, that you should really be looking at Android 5 at the very, very earliest. If you're looking for Bluetooth Low Energy support, have a look at the pie chart on the Android developer web content, and you'll see information there. We don't publish that information, but to be perfectly honest, in terms of smartphones, it's pretty much all smartphones. Okay, I don't remember ever having encountered a smartphone that didn't have Bluetooth Low Energy available on it. More generally, not just smartphones, there are like 10 million devices shipped every single day. And that figure is 2 years old. I'm out of date on that figure. It's been increasing since I first heard that, I think. Oh, that's very kind. Thank you very much, Dave. Dave said something nice, so Dave's my friend now. What sort of devices can we expect to support the alternative PHYs? Is it something very new that we can expect only the latest and greatest devices to support? Bluetooth 5, as opposed to 5.1 and 5.2, came out about 3 years ago, so it is normal to find Bluetooth 5 on smartphones these days, and it has been for at least a year. What I've noted is that you tend to find the LE2M PHY is supported as well as LE1M, so the 1 megabit and 2 megabit version, but not necessarily the LE coded PHY for longer range. These are all optional features of Bluetooth, so it's up to manufacturers to decide what they want to support. Okay, another anonymous question. Do you know if any changes are planned for the Android Bluetooth API, like having the binding pairing handled by the system instead of the app? As it stands now, it seems designed to fail when HTTP does all that just better. Okay, interesting one. That's gone off. Oh no, I thought it went off screen there. I don't know of changes planned because we're not involved in APIs at all for any platforms. That's not our role. Binding and pairing on Android is in fact handled by the operating system. On iOS, it's not. On iOS, pairing is triggered when an application first tries to do something that has security flags attached to it, like a characteristic, and that triggers the pairing process. On Android, you can pair directly through the settings screen, or you can trigger it through an application. Not sure about the design to fail, haven't personally had any problems there. Enrico, how can we implement a mesh proxy server? Go to bluetooth.com, go into resources, click on study guides, and we have a study guide specifically about this topic. And I should have said this, it includes sample code. In fact, the application I demonstrated, the code for that application is right there. So the theory is explained, code is provided, and you get to do some hands-on coding to kind of cement the information in your head. Anonymous wanted to just summarize and check in order to improve speed of the application. So this is data transfer as measured at the application layer. Yes, request a higher MTU, a high connection priority, select the LE2M PHY if it's available, use new devices which have the LE packet data extension feature. Yeah, that's about it. Quintin, thank you so much for the feedback. I'm glad you found that useful. I'm sure these slides will be available in some form, but the organisers will deal with that. Thank you ever so much, everybody, for attending today and for your questions. Thank you. It's looking